All right, why don't we get started? Today we're going to move on to, finally, the most realistic market structure. We talked about perfectly competitive markets, and how that was a very useful extreme example to help us think about economic efficiency. We then flipped over to talk about the somewhat more realistic case of monopoly, but still very few markets have only one participant. A true monopoly is rare in the private market. What most markets are marked by are probably more features of oligopoly, which is a market with a small group of firms competing with each other, but with barriers to entry that keep out an unlimited number of firms. Let's think about these as markets where there are some barriers to entry, so firms just can't cautiously enter and exit like they could in our IBM Dell example, but where there's small enough barriers to entry that a few firms have gotten in, not just one. So it's not a natural monopoly. It's not like the only one firm can be in there. Multiple firms are in there, but they only know they have to compete with each other, not with the big wide world. Okay? So for example, the classic example in the oligopoly industry would be the auto industry. Auto manufacturers clearly compete. Clearly, if you watch any sporting event and watch how much advertising that goes on, they clearly are competing with each other. They're comparing to each other all the time. But there's only most of the cars in the world are produced by fewer than 10 auto manufacturers. The notion that we have in a perfectly competitive market of thousands of sellers selling identical goods is clearly not right when it comes to buying a car. So that's sort of the model we're going to want to focus on for the next few lectures. Now, within an oligopoly market, whenever we think about this market, we want to start by noting that within this market, these limited set of competitors can behave in two ways. They can behave cooperatively or non-cooperatively. Okay? Cooperative means that they can form what's called a cartel. So when there's an oligopoly market and the firms cooperatively get together and make decisions, that's called a cartel. The most famous example of which is OPEC, the Organization of Petroleum Exporting Countries, which are the set of countries that control about 2/3 of the world's oil, led by Saudi Arabia is the major player in OPEC. It's a cartel of about a dozen nations. And what they do is they control the vast majority of the world's oil reserves. And by behaving cooperatively, they essentially turn themselves into a monopoly. OPEC acts as if they've got the monopoly in oil. Certainly, they used to. Now it's getting harder. Other non-OPEC countries are starting to produce more oil, and it's breaking down. But for a long time, they were essentially the cooperative producer of oil, and they acted essentially like a monopoly, and they made lots of profits like a monopoly. They kept prices high, they kept production inefficiently low, and they made lots of money. Okay? However, that's a great outcome for producers. But as we'll talk about next time, it's actually a hard outcome to enforce. It turns out to be hard to keep cartels together. And so typically, oligopoly markets behave in a non-cooperative way, with the participants competing with each other, not cooperating with each other. And in this case, you can actually get them driving their profits down far below the monopoly level, and indeed, perhaps even all the way to the competitive level. So you can think about markets as a competitive as one extreme, and the monopoly is the other extreme, oligopoly in between. A cooperative oligopoly market like cartel will end up close to the monopoly outcome. A non-cooperative market will end up somewhere in between. And we're going to model today's where in between do they end up. Okay? Now, to think about this, we're going to have to turn to a tool which has really become a dominant tool in economics over the last 40 years, which is the tool of game theory. Game theory. So basically, we could think of we're going to think of oligopoly firms as engaging in a game. Okay? And as with any game, you need to sort of know two things. One is you need to know what's the strategy. And the second is you need to know when is the game over. Kind of what's the equilibrium. And that's sort of essentially what you do with any game. And so basically, what we're going to do, the key with game theory is that we are going to define the equilibrium, and that's going to yield for us the strategy that players are going to use. However, equilibrium in a game is not well defined. It's not like a set of rules that are printed out like Monopoly. In a non-cooperative oligopoly market, the equilibrium, you have to actually come up with different concepts of what equilibrium is. There's not a hard and fast scientific rule. And the typical one that's used is called the Nash Equilibrium. The Nash Equilibrium, named for the John Nash, the famous mathematician, who economists have claimed as their own, even though he's really a mathematician. But we gave him the Nobel Prize anyway. And you know, if you think of him as an economist, probably one of the most famous. You know, you all know about the movie and book Beautiful Mind. He is basically the father of game theory. Okay? So basically, what is the Nash equilibrium? The Nash equilibrium is defined as the point at which no player wants to change their strategy given what the other players are doing. So the point at which no player wants to change its strategy given what the other players are doing. So in other words, every player is happy with where they are. Given what every other player's decided, I'm happy to do what I've decided. So I've got a strategy, and given the strategy other players are using, if I'm happy with my strategy, then that's an equilibrium. Okay? So this is a super abstract concept. So let's illustrate it with an example. And the classic example of game theory is the prisoner's dilemma, which many of you, I'm sure, know about, maybe even most of you, but let's just go through it. This is the thing from the old cop movies you see where they arrest two guys, and they put them in separate rooms, and they basically interrogate them separately. Okay? And what they say is they're put in separate rooms, and let's say that these guys get told the following. They each get told separately the following thing. They get told that right now, if nothing else happens, there's enough evidence to send them each away for 1 year. However, they're told, if they turn on their friend and say their friend's guilty, then they go free and their friend gets 5 years. If their friend turns on them, then the friend goes free and they get 5 years. But if they both turn on each other, they both get 2 years. Okay? Setup is if they both stay silent, they both get 1 year. If one turns, then that person gets to leave and the other person gets 5 years. But if they both turn, then they each get 2 years. So how do we think about decision-making in that context? The way we do that is we write down what we call a payoff matrix. We sort of write down in matrix form this decision. So let's think about what a payoff matrix looks like. Up here, prisoner B. And here you have prisoner A. Prisoner A. And prisoner A can remain silent, or they can talk. And prisoner B can remain silent, or they can talk. Okay? And then we just write down what are the outcomes, or the payoffs, from these different strategies. So if prisoner A says nothing, and prisoner B says nothing, then A gets 1 year, and B gets 1 year. If prisoner A says nothing, and prisoner B says, oh yeah, prisoner A is definitely guilty, then prisoner A gets 5 years, and prisoner B gets 0 years. If the opposite happens, if prisoner A says, yeah, B's guilty, and B doesn't say anything about A, then A gets 0 years, and B gets 5 years. But if they both say the other one's guilty, then they each get 2 years. Okay? That's the payoff matrix. Okay? And now we want to ask, given this payoff matrix, what is the right strategy for each prisoner to pursue? And the way we do this in the Nash Equilibrium concept is we look for a dominant strategy. Is there a strategy that I would pursue regardless of what the other person does? And if there is, I'll pursue that. Because remember, the Nash Equilibrium concept is, what do I want to do given what the other person's doing? If I have a strategy I want to do no matter what the other person's doing, then I'll do it. So when I ask, is there a dominant strategy? Is there a strategy that is the best thing to do no matter what the other guy does? Okay? Well, clearly, if they're cooperating, if these were stupid police and they sat in the same room and told us and then left, the two guys could cooperate and say, well, clearly the dominant cooperative strategy is for both of us to remain silent. That's the dominant cooperative strategy. And as a team, we only get 2 total years in jail, where everything gives many more years in jail. So if they're buddies and they trust each other and they cooperate, then that's the closest right strategy. But let's say the police are smart and put them in separate rooms. Okay? Well, what's the dominant non-cooperative strategy? What is the strategy that A or B, say A should produce? Yeah. Why?
Either way, you're going to get less years. Like if the other person's silent and you talk, you get 0. And if they talk and you talk as well, you get 2 versus 5.
Exactly. For prisoner A, in this first row, compare the first row, first column. Let's say prisoner B is silent. Then clearly you're better off talking than not talking. 0 rather than 1. Let's say prisoner B talks. Then you're still better off talking than not talking. So no matter what B does, you should talk. Likewise, prisoner B, no matter what A does, B should talk. So the non-cooperative equilibrium is actually this outcome. They both end up talking. You get sort of a race to the bottom. The non-cooperative outcome is much worse than if they could have cooperated. Okay? So basically, what you get is that the non-cooperative equilibrium is always worse for the players than the cooperative equilibrium. And this was like an unbelievable insight of Nash. Before Nash, we always thought competition was always and everywhere good. We thought more competition is better for the reasons we taught you in the first 10 or 12 lectures of this class. Nash was the first one to say, no, actually competition can be bad, cooperation can be better. I don't know if you remember the scene in A Beautiful Mind where they're picking up girls in the bar. And he describes sort of basically a Nash strategy, okay? How competition will lead to the worst outcome, okay? And basically that's what you see here, that competition can actually lead to a worse outcome than cooperation. And that was really sort of Nash's sort of brilliant insight. Now, this is sort of a cute example with prisoners, but actually, for 2 points. First of all, this generally shows you how you do game theory with Nash equilibria. Basically, you look at the payoff matrix, you find the dominant strategy, and then you find where those dominant strategies intersect. And here, the dominant strategies intersect at this cell. Therefore, that's the equilibrium. Okay? So that's basically how you do game theory in a game theory kindergarten level. Okay? You look at the matrix, you find each player's dominant strategy, and you find the point at which those dominant strategies intersect. And at that point, that's the equilibrium. Now, that's all well and good for sort of a simple example like this, but let's actually apply it to an economics example. Let's think about advertising. So think about Coke and Pepsi. Okay? Now, right now, let's think about their decision to advertise. Now, obviously, this is a simple problem. Obviously, Pepsi should just be illegal because Coke's just way better. But sadly, it's not. And sometimes I have to drink Pepsi, and I'm very sad. But nonetheless, in the real world, we have Coke and Pepsi, and they have to decide how much to advertise. Now, the dominant cooperative strategy would be to say, look, advertising costs us a ton of money. Let's just split the market. Let's have a monopoly market and just split it. We're close to splitting it anyway. Coke's got some more of it. We're close to splitting it. Let's just split it. Yeah.
Wait, didn't he actually do that?
What?
Didn't he actually do that? Because I remember there are like places that Coke and Pepsi aren't allowed to both sell in the same place.
Okay, but that's different than the cooperative. That's imposed not by Coke and Pepsi jointly. That's imposed by Pepsi saying to a university campus, for example, we will cut you a better deal if you'll agree not to sell Coke. That's not cooperation, that's competition. Okay? So there's a cooperative strategy, but what if they don't cooperate? Okay? Well, let's imagine we have the following payoff matrix. Okay? You've got Pepsi up here, and they can advertise or not advertise. And you've got Coke here, and they can advertise or not advertise. And let's say the payoff matrix is the following. Let's say if both Pepsi and Coke, let's say the total amount of profit to be made is 16 billion, whatever units you want to make it, 16 billion. Okay? And let's say if there's no advertising, Coke gets 8 and Pepsi gets 8. Okay? But let's say advertising costs money. It costs 5 billion. So let's say if they both advertise, then they still end up splitting the market, but they only make 3. C equals 3, P equals 3. So if they, I'm sorry, it's the obvious. Advertise, yes, you're right. C equals 3, P equals 3. And here C equals 8, P equals 8. Okay? So basically, they are, so basically of a situation where they both end up splitting the market either way, but they just split a smaller net profit if they advertise. So clearly they'd rather be here than here. But what happens in the off-diagonal elements? Well, let's say also that if Coke advertises, but Pepsi does not, then let's say Coke ends up making 13 billion, and Pepsi ends up making minus, if Coke advertises and Pepsi does not, I just flipped my heat, and Pepsi makes -2. They actually lose money because they have fixed costs and they don't sell anything. Nobody buys Pepsi, they lose money. And let's say if Pepsi advertises and Coke doesn't, then Coke makes -2 and Pepsi makes 13. Okay? So actually, if you don't advertise, you're really screwed. And the other guy does, you're really screwed. Yeah? This doesn't include the cost of advertising. But it's just Coke, gets a huge market, expands its market. Okay? So now, let's play the game. Well, now let's say you're Coke. You say, well, if I advertise and Pepsi advertises, I make 3. But if I don't advertise and Pepsi advertises, I make -2, so I should advertise. If I advertise, Pepsi doesn't advertise, I make 13. If I don't advertise and Pepsi doesn't advertise, I make 8. So either way, my dominant strategy is to advertise. And likewise, Pepsi does the same thing. It's actually, I screwed up writing this compared to my notes, but it's good because it shows you, I flipped the matrix, but the logic is the same. It helps you sort of not just memorize cells in a matrix, but learn the logic. The point is, either way, the dominant strategy is to advertise. So they both advertise. So real-world example of how you can end up. Now, someone mentioned Pepsi and Coke do this. Actually, there was an industry that did this. So when I was a kid, you never, ever saw ads for liquor on TV. There were beer ads and wine ads, but no hard alcohol ad. No bourbon, no whiskey, no nothing. Gin, all those Captain Morgan's ads we see now, they didn't exist when I was a kid. But it wasn't because of the law. It was because the hard liquor industry cooperatively agreed none of them would advertise. So they actually imposed the cooperative equilibrium, and then that broke down. I don't know the story of how it broke down. But some it broke down, now they all advertise. And they're probably all worse off than they were when they just didn't advertise. Okay, we'll talk next time about why it probably broke down. I don't know the stories. Well, I have a rough sense, and we'll talk about that next time. But this is the point of how a non-cooperative equilibrium can drive you to a bad outcome. Okay? Now, basically, this doesn't just apply to prisoners or business, it applies to people too. So let's say poor Hector back there has had a fight with his girlfriend. Okay? And they've had a big fight. They've been going a little while. They've had a big fight. And Hector's got to decide, do I apologize or do I wait for her to apologize? Okay? Well, the last thing Hector wants is to go up there and apologize, have her say, forget it, I'm breaking up with you. That'd be the worst. Okay? If he knows she's going to be like, oh, I'm sorry too, then he'd be happy to do it. But what if he goes, she says, no, I'm breaking up with you? Well then, and she's thinking the same thing. So what happens? They break up. Okay? We've been through this many times in our lives. This is the non-cooperative strategy. Okay? Basically, if you know what the other person is going to do, your dominant strategy is to be an asshole. Okay? And basically, that happens a lot in the context of the real world. Okay? So now, we have this sort of sad-sounding outcome that basically game theory leads to bad outcomes for producers, at least. But this is what's exciting about game theory. So when I went to grad school back, when dinosaurs roamed the earth, game theory was sort of taught barely in the sequence. It was sort of like an extra course, taught a little bit. Now it sort of dominates the teaching of microeconomics in economics. And it doesn't dominate, but it's a whole like component of our core microeconomics education, because it's given such a cool set of tools to think about these decisions. Now, I can't give you even 1% of the flavor of game theory. If you want to learn more, I highly suggest you take 1412, which is our game theory class, and you can learn a ton. But let me use sort of one interesting wrinkle of the kind of things game theory can do to go beyond this. And that's to imagine that Coke and Pepsi are not playing a one-shot game, but a repeated game. Repeated game. Okay? So now imagine that Coke says to Pepsi the following: I promise to not advertise as long as you don't advertise. But if you ever advertise, I will advertise forever. Okay? Coke says to Pepsi, I promise not to advertise as long as you don't advertise. But if I ever catch you advertising, I'm going to advertise forever. Okay? So now think about Pepsi's choice in period 1. Pepsi's choice in period 1. In period 1, they could say, ha, stupid Coke. I'm going to jump on them and advertise. They promise they're not going to advertise. I'm going to make, so if Pepsi advertises, they're going to make 13 in period 1, right? Because Coke's taken themselves off to the side. But after period 1, they're going to make 8 forever. No, I'm sorry, they're going to make 3 forever. Because Coke's going to advertise, they're going to advertise, then they break down to the non-cooperative equilibrium. Okay? If Pepsi advertises. Now what if Pepsi doesn't advertise? As long as it doesn't advertise, then it gets to deal with Coke, so it makes 8 forever. So now we'll talk later in the course about how you combine numbers that happen at different times. So trust me, 8 forever is a way better deal than 13 than 3 forever. Okay? So actually, by having this be a repeated game, Coke has solved the prisoner's dilemma. It's essentially imposed a cooperative equilibrium on the problem. Okay? So that's how a repeated game can fix this. But, this is where game theory gets really exciting, that only works if this game never ends. Because once Coke or Pepsi thinks there's an end to the game, the entire thing breaks down. Okay? So imagine, for example, that Coke makes the offer to Pepsi, but Pepsi's worried that in 10 years the government's going to outlaw soda. Okay? The government, said, look, we're heading that direction. Soda's going to be legal in 10 years. So I don't want to do this. So in that case, no, I'm sorry, not that I want to, so I have that in my mind. So Coke offers the deal. Now, what do I think? Well, let's think about Pepsi's decision in the 9th year. They've made 8, 8, 8, 8, 8, and they get to year 9. Now, in year 9, they know that next year there's no more game. So what should they do? Advertise. Grab the 13 in the last period. Because Coke can't punish them because the game's over. But Coke knows this. So what's Coke going to do in the 9th year? Advertise. It's going to advertise. So they're both going to make, so they're both going to make 3. Well, if Pepsi knows Coke's going to advertise in the 9th year no matter what should Pepsi do in the 8th year? Advertise. And if Coke knows Pepsi's going to advertise in the 8th year, what should Coke do? And so on, and it ends up that they both advertise all the way through. So the game breaks down if it's an end. This is really kind of neat. And this is what game theory is all about, is how do you think through these more complicated scenarios that are much more complicated than the prisoner's dilemma, and actually think about how firms and individuals might actually behave. Yeah?
Wouldn't it also be advantageous to if you said to advertise the first year and set up these contracts, kind of like we were talking about earlier, so
Sure, that's much more, and once again, that's what you cover in a field course like game theory. Is what about alternative forms of contracting with exclusionary contracting, what we call tying in contracting? That's great, and they would, but that's why you got to take 1412. Okay? Yeah.
Would it be a better outcome if they cooperated and switched periods of advertising? Like for the first period, like they get 13, we get -2, and the next.
Yeah, the way I've set this problem up, if they could commit to that, that'd be right. But you'd have to commit to it, because then the period that Pepsi promised to take off, if they actually advertise that period, then Coke's screwed. So that would work as a repeated game solution. but it wouldn't work as a non-repeated game. So it would work as an infinite repeated game, but not a non-infinite repeated game. Okay, good question. Okay, other questions? All right, so that's the basics of game theory. That's just a taste for the excitement that you can live with game theory. But in fact, in economics, we like to write down these fun examples, but we really prefer to do math. So let's actually think about the math of how we take game theory concepts and put them in practice. And the way we do that is through the concept of the Corneal Model. The Corneal Model of non-cooperative oligopolies. Okay? So it's the Corneal Model of non-cooperative oligopoly. It's the standard workhorse model that takes this intuition and puts it into the kind of optimizing math we've been doing so far this class. Okay? So now let's imagine a non-cooperative case. But now let's imagine there's not just two choices, but realistically there's a whole set of choices. Okay? Then how would you behave in that case? So let's imagine that there's two airlines, United and American. United and American, so we're going to have an oligopolistic two-firm airline industry. Obviously, the math can extend to more firms, but just to start now, and I'll talk about that next lecture. But for now, imagine a two-firm industry, United and American. And because of the hub and spoke system we discussed last time, let's imagine they're the only two folks that go from Boston to Chicago. Okay? Because this hub and spoke system, the only folks that go from Boston to Chicago are United and American. They do, in fact, dominate that line. So let's imagine the only folks. And say no other firms can compete on this route because they can't get slots at the airport. So the question is, how do these firms decide how many flights to run? It's not just advertise don't. It's literally a continuous decision of how many flights to run every day and how much to charge. Okay? They've got to make that decision. And the Nash equilibrium here we call a Corneal, the sort of subset of Nash for this example is called the Corneal equilibrium. And the Corneal equilibrium exists when a firm chooses a quantity such that given the quantity chosen by the other firm, they don't want to change. So a firm chooses essentially a profit maximizing quantity given the quantity chosen by the other firm. Okay? And if that profit maximizing quantity, okay, then that you're in Corneal equilibrium if you have chosen a quantity that is profit maximizing given what the other firm is doing. Okay? So basically, how do we actually carry this out? Okay, let's talk about the steps. Okay, so the first step, I'm going to talk intuitively about the math, what we're going to do, and then I'm going to talk mathematically and graphically what we actually do. There's essentially three steps in solving for the Corneal equilibrium. The first is ask how your demand changes when some of it's absorbed by other firms. So the first is solve for your residual demand function. What does your demand curve look like given what the other firm does? That's step one. Step two is then you develop a marginal revenue, which is a function of the other firm's quantity. Little q, it's multiple firms. Okay? The other firms, that's really bad, hard to read, the other firm's quantity. So it's your marginal revenue is a function, typically, it's a function, of both your quantity and the other firm's quantity. A function of both your quantity and the other firm's quantity. We develop marginal revenue as a function of your own quantity. We know how to do that. Now we're going to develop marginal revenue as a function of your quantity and the other firm's quantity. Then you simply set this marginal revenue equal to marginal cost, and that delivers you a conditional answer. That delivers you your optimal quantity as a function of the other firm's quantity. Okay? Well, that doesn't do us a whole lot of good, except there's two firms. So the fourth step is we do the same thing for the other firm and get the same kind of equation. Then what do we have? Two equations and two unknowns, so we solve. Okay? So what we do here is essentially the same thing we did before, but now your marginal revenue is not just a function of your own quantity, it's a function of the other guy's quantity. Same with the other guy. That gives you two equations and two unknowns we solve, and the point at which both firms are happy is the Corneal equilibrium. Okay? So let's actually, that's confusing, so let's actually look at that. let's start, we'll do this both graphically and mathematically. Let's start with figure 13.1. Okay? To make things easy, let's start by imagining that American Airlines is a monopoly. Let's start with a world with an American Airlines monopoly. Okay? And let's say that the demand function is P equals 339 minus Q. That's the demand for flights from Boston to Chicago. Okay? And let's say that the marginal cost, to make life easy, I could have a cost function to make your life difficult, and maybe someday I'll do that. But for now, I'm going to make your life easy. Let's just say there's a flat marginal cost of $147. Okay? I'm not going to make life difficult with solving for marginal cost functions. For now, let's just assume a flat marginal cost of 147. No matter how many flights they do, it's $147 per passenger. So if you're a monopolist, how do you solve this problem? Well, first you derive your marginal revenue function. Well, what's marginal revenue function? Well, revenues is P times Q, which is 339Q minus Q squared. So your marginal revenue function is 339 minus 2Q. That's your marginal revenue function if you're the monopolist. What's your marginal cost? Well, I already said it's 147. And then you just solve. And when you solve that, you get that Q, the optimal quantity, is 96 flights. And then how do you get the price? How do you get the price monopoly problem? How do we know what the price is? Yeah?
Where the quantity intersects the demand curve.
You got to plug it back into the demand curve. You got to take that quantity, plug it back to the demand curve, so the price is 339 minus 96, or 243. Okay? So I just solved the monopoly problem quickly, but that's what we've done already in this class. And you can see that in the graph here. Okay, in figure 13.1, you've got a demand curve, which is P equals 339 minus Q. You've got a supply curve, which is a flat marginal cost at 147. You develop a marginal revenue function, which is 339 minus 2Q. As in our previous example, that's just basically an inward shift of the demand function. That intersects marginal cost at 96 flights. Okay? We have this as 1,000 passengers per quarter. It doesn't really matter. The units, ignore the, it's just all standardization. Okay? And then to get the price, you read it off the demand curve. You say 96 flights means a price of 243 per flight. Okay? That's what we do if American was a monopolist. Now, however, American's not a monopolist. American deals with United. And American doesn't know what United's going to do. So what does American do? Well, let's say American now has to deal with the fact that it now has to recognize that the demand, it's got its own demand function, QA, which is the total quantity in the market minus QU. Okay? So it has a residual demand function, which is the total demand in the market minus what United sells. Okay? So suppose, for example, American's got a spy inside United. And American says, I think United's going to fly 64 flights. Okay? So imagine American thinks United's going to fly 64 flights. Well, in that case, it would say, well, in that case, if they're going to fly 64 flights, then my demand function is P sub A equals 339 minus Q sub A minus 64, right? Because the big quantity, okay, the big quantity is little qa plus little qu. So my demand function is 339 minus Q sub A minus 64. Okay? Or in other words, my residual demand function is that P sub A equals 339 equals 275 minus QA. So if I think United's going to fly 64 flights, then my effective demand function is 275 minus Q. And then I'm done. Then I just solve for what would I do as a monopolist, given the other guy's flying 64 flights. So you can see that in figure 13 too. Okay? So I have a demand function. I say, well, if United's going to fly 64 flights, that demand function gets shifted in by 64. And then I do the same thing I did before. I solve for marginal revenue. Okay, I solve for marginal revenue. And I intersect that with marginal cost. That's going to happen at 64 flights and a price of $2.11. Okay? So basically, it's the same exercise. It's not that hard. You just first take out what United's going to do. The problem is American doesn't have a SPY. They don't really know what United's going to do. They have to essentially develop a strategy given the possibilities of what United might do. They have to say, look, I don't know what Q sub U is. So I have to devise my optimal strategy given Q sub U. Okay? In other words, I have to simultaneously solve for what I would do at every possible quantity United would sell. I have to solve what I would do for every possible quantity United would sell. And we call this developing your reaction or best response curve. Your reaction curve or your best response curve, which is what is the best thing to do given what the other guy's doing. What is the best thing to do given what the other guy's doing? Okay? You can see that in figure 13.3. We show how that works. Okay? That shows best response curves. So for example, look at the intersection on the y-axis where the red line hits the y-axis. That was our monopoly equilibrium. Where the blue line hits the x-axis. My bad. We're doing American. Look at where the blue line hits the x-axis. That is assuming 0 United flights, right? Where the blue line hits the x-axis is where there's 0 United flights. Well, we know what American would do there. They would fly 96 flights. We already solved that. Now look at the point where United is flying 64 flights. Well, we also know what American would do then. We know that we solved in the previous figure, they would then do 64 flights. And in general, what that blue line is for every quantity that United flies, what does American want to fly? Okay? Now, let's actually do, and so meanwhile, United is doing the same mathematics. Imagine, to make life easy, and we'll almost always do this to make life easy, imagine United has the same marginal cost as American, and obviously faces the same market demand curve. Well, then literally their math is totally symmetric. If American wasn't in the market, you'd have where the red line intersects the vertical axis. If American was flying 0, United would fly 96 flights, because their problem is identical to American's monopoly problem. Likewise, so that the red line is United's best response curve. So we've graphed for every possible amount of flights that United does, what's American's optimal amount of flights. We've solved for every amount of flights that American does, what's United's optimal amount of flights. Where those lines intersect is the Corneal equilibrium. Why is that the Corneal equilibrium? Because at that point, both firms are doing the best they can given what the other firm's chosen. Or in other words, to say this is, given what the other firm's doing, neither firm wants to deviate. The profit maximizing choice is to be where they are, given the other firm's behavior. Okay? So basically, the Corneal equilibrium is the only equilibrium that's possible in this market. Okay? So, and why is that? So for example, imagine that American came in and said, look, I like doing 96 flights. I love being a monopolist. I'm just going to do 96 flights. And I'm going to charge, I'm going to do 96 flights, I'm going to charge $243. Well, in that case, United, would happily come in at $242 and undercut them and sell lots of flights because that's still well above marginal cost. So that's not an equilibrium because United and American are choosing different outcomes. It's only equilibrium if they're both to the point where the same outcome makes them both happy. Okay? So that's the graphics. Let's actually do the math here. Let's do the Corneal math. Okay? In general, the residual demand for American is that P equals 339 minus QA minus QU. Okay? Remember, big Q is QA plus QU. So since the demand function is 339 minus big Q, I simply broke big Q into QA and QU. Okay? Stop me if this is all unclear. Simply broke up the big Q into those two components. So that means that American's revenue function, let's call revenue A, revenue for American, is 339 times QA minus QA squared minus QA QU. This is a new term. This was the old revenue function we had when they were monopolists. Now I've got this new term that didn't exist before. So that means their marginal revenue for American is now 339 minus 2QA minus QU. So now their marginal revenue is actually a function not only of their own behavior, but their competitors' behavior. That's the new marginal revenue function. Okay? Now, but the profit maximization rule is the same. You just set that equal to marginal cost. So you set equal to 147, and you solve. And what you end up getting is that Q sub A star, the optimal Q sub A, is 96 minus 1/2 QU star, or QU. QA star is 96 minus 1/2 QU. If you solve this equation, that's what you get. That's 1/2. Jesus. 1/2 QU. So now we have the optimal quantity, but it's a function of what the other guy does. That's a problem, except that we do the same math for United. Now, if the problem's symmetric, you don't have to do the math again. You know the best response function will be symmetric. But that won't always be the case. So I'm going to use a shortcut here of saying the best response function for QU is Q star U equals 96 minus 1/2 QA. Okay? So I've just written down their best response function. This corresponds to the graph. Look at so Q star A, that's the blue line. It's 96 minus 1/2 QU. Okay? Q star U, that's the red line. 96 minus 1/2 QA. That's their best response function. Now, once again, to remind you, I could simply skip to this step, but normally you'd have to solve through for both firms because they might not have identical best response functions or symmetrical best response functions. Well, now we're golden. We have two equations and two unknowns. We know how to deal with that. And you solve them, and you get that QA star equals QU star equals 64. You solve those two equations and two unknowns. Okay? So 64 is the solution to that system. What's the price? Someone raise their hand and tell me. What's the price? Without looking at the graph. Yeah. And how'd you get that? You've got to plug in 64 twice. A lot of people get this wrong. They'll say, oh, 339 minus 64. But no, it's 339 minus 128. Because they're each flying 64, and the price comes from the total demand in the market. So the price is 211. Okay? That's an important mistake to avoid. A lot of people get here, they'll be super excited, they're tired, they throw the 64 back in the demand equation. But remember, demand's a function of the total market. If symmetrically they're each doing 64, then the price is going to be 211. And that is the Nash or Corneal equilibrium. Both firms are happy to fly 64 flights at a price of 211. Neither firm wants to deviate. And you know that because you've maximized their profits. And the profits for American are maximized. When United is flying 64, the profits for American are maximized at flying 64. When American's flying 64, the profits for United are maximized at flying 64. Therefore, that is the Nash or Corneal equilibrium. Okay? Now, when we get to reality, things might not always work out so neatly. Things might not be symmetric. You might also not have an equilibrium. How could you not have an equilibrium here? How could that happen? Graphically, what would that mean? Yeah?
Response curves don't intersect?
Yeah, the best response curves might not intersect. You might not get an equilibrium. We don't know what the hell to do then. All chaos breaks loose. Okay? But you might not get an equilibrium, okay, in this market because the best response curves might not intersect. Okay? In reality in life, you can have funky best response curves that are nonlinear. You can have multiple intersections. You can have multiple, we call multiple equilibria. And then it becomes an indeterminate problem, and you have to figure out which equilibrium they settle at, and that involves higher order mathematics that you talk about in more advanced classes. So this is sort of the simplest, easiest case. A symmetric case with linear best response functions intersect is your easiest case. But in general, the general way to solve this is the same, which is to use the principle of game theory. Look, go back to the prisoner's dilemma. Okay? All we're doing here was creating best response functions. It's just there wasn't a line, it was just a point. The best response function was what we laid out here. All we did with this United American example is go to a continuum and develop best response function around just the best response point. Okay? Yeah.
If the Nash equilibrium is always worse than when they're cooperating, why is it so hard to maintain a cooperative model?
We'll talk about that next time. Other questions? Okay, let's stop there. We'll come back next time. We'll talk about why don't we all just get along like Mr. Rogers wants.